Hello, welcome to the Distributed SQL Summit. The title of this session is a bit long because I will present a feature that exists in many traditional databases with different name. Loose index scan, skip scan, jump scan, and we call it hybrid scan. Basically, it is a kind of scan on an index that is optimized to reduce the remote calls to the server nodes in YugabyteDB. I'm Frank Pacho, I'm developer advocate at Yugabyte. And for this session, I will take an example with a simple time series example. There are two reasons why I wanted to present this. The first one, of course, this is a very interesting feature for performance, losing the scan. And another reason is that I've heard bad rumors from many competitors about their misunderstanding on the Yugabyte architecture. So we will come to that later. For the moment, we'll see an example with a time series. And maybe before going to the slides, let me show you quickly an example of this feature. I have a table here with 31 million rows. And I will run a select distinct on it to see the number of distinct value. So let me check the structure of my table here. It is a very basic table with no secondary indexes and only a primary key, where basically I store for a device ID at a specific timestamp value. And you can see that I do not have a table of device IDs. If I want to get the list of device IDs, I have to scan this table. And this is what I'm doing there, scanning the table for distinct device ID. And this device ID is just the leading column in the primary key index. This, without a loose index scan, has to scan the whole table. Here, I will explain to show what happens. So I'm doing an index scan on the primary key. The table is stored in the primary key in Yugabyte. There is no heap table. There is no B tree. Everything is stored in LSM tree, and the table is stored in the primary key. And basically, I scan an index on 31 million rows, but the skip scan just reads the distinct value, and you see that it has read only 32 rows there. And the calls to the storage are minimal, just 2 calls for that. So that's the idea of the feature, and it helps many queries. So that was an example with a select, sorry, they don't want to print anything. That was a select distinct. It can help also when you have a condition on a column that is not the first column of the index. Usually, you can filter only when you have the prefix of the index in the where clause. Here, event TS is the second column of my primary key, and you can see how this is fast. Timing on. Just a few milliseconds, 100 milliseconds. And for the distinct, that was also a bit the same. So like scanning many rows and getting all distinct value, or a specific timestamp, but much faster than scanning the rows. So that's basically the feature I want to show you and explain. So basically, this is how I have created the table: a time series, device ID, event, value, and my primary key, starting with device ID, event, timestamp. Then I have inserted some rows. In this example, I insert just 1 million row, so 10 devices and 100,000 rows. So that's 1 million row. If you want more, you repeat it. Here for the slide, I repeated 10 times, so 10 million rows. And the most important thing, as I mentioned, is that Yugabyte stores everything in the primary key, and that's much faster when you have no secondary indexes. So the count, as we have seen, is very fast. And the count is not so fast because it has to scan all the rows and count them. So here in this example with 10 million rows, the count takes 13 seconds because it has to scan all the rows. Even if we can see partial aggregate, this is pushed down to the storage. All nodes are counting their rows, but still have to look at them, all of them. And without this feature, hybrid scan, loose index scan, without this feature, then we would have to scan the same rows and then get a distinct, usually by sorting them or hashing them. Here, you can see how it is fast, much faster than scanning all the rows. That's the main point. Here, the time depends on the number of distinct value, doesn't depend on the number of rows in the table. So this is really scalable. You see the same plan as if it scans all the rows, but behind the scene, it just keeps many rows that are not useful when you want only the distinct value. And the other example I had was with a predicate on the second column of the index. And again, this is fast. Without this feature, you need to create a secondary index that starts with the timestamp if you want an index access to those 10 rows with a specific timestamp. Here, you don't have to. So that's also the big value of it. The less indexes you have, the better it is. And one index can serve many different use cases thanks to this feature. So again, you see an index scan, but it can skip on the different device ID to get directly to the timestamps that we want. Another case where this feature kicks in, when we select, so device ID is the first column of the index. So if I select device ID equals something, then the index can help to find directly the rows for that. But if I have multiple points, many databases have to look many times at the index. And here, thanks to the skip scan, even if I have a big list of values, in one scan, it will skip to go directly to the different values. And again, this is fast, just in milliseconds, very different than the time it takes to scan all rows. So again, in the plan, this is still an index scan. It is an optimization behind the index scan done at the storage level at DocDB, the distributed storage and transaction layer of YugabyteDB. Basically, the plan here comes from the Postgres layer, the SQL layer, and the optimization goes behind. Of course, there are some information that is pushed down to the storage to be able to do that. So let's look quickly how it works. In YugabyteDB, we store, so first, the tables are sharded to multiple tablets to be able to manage small chunks of data and replicate them. That's for high availability, that's for elasticity, scalability. Each of those chunks that we call tablets are stored in a LSM tree. So no heap tables, no B tree. LSM tree, that is a sorted structure, so perfect for an index. The idea of the LSM tree is that all inserts are appended and then they are merged. So they are appended in memory. With that you have fast ingest, and then they are flushed to files, SST files, and then those files are merged when you query for a specific value or during compaction to have less files. So that's how it works, and the code base for this part, for the storage of those tablets in YugabyteDB, the code base is based on RocksDB, but with a lot of enhancements. This one is a new iterator that has been made on top of the RocksDB code specifically for Yugabyte. So you can think of each tablet as an ordered structure, the primary key and the table columns. I do not look at indexes there. I have everything in the primary key. This feature, of course, works also for secondary indexes. But here I have the table with only one index, the primary key, and the table is stored into it. So there are two operations mainly when you read data from RocksDB, from this LSM tree. The first one is seek it into a specific point. So you have a query, you have a where clause that can be an inequality with a value or an inequality starting at a value. You seek directly in the structure. In my case, if you remember, I had a query where I can still show it. I had a query where I started from the beginning, the lowest possible value for this UID, and going to the end. So this is why in my diagram, I seek to the beginning of it. But of course, the same happens with a small range. Here, I just wanted to show you how it is fast when the range is large, many millions of rows. So an index scan seeks to a specific value and then read the next value, the next rows. But the point is that when you have to read for another value, without this feature, it will be another call, another seek. Here, we can just skip to seek to another point. And that's exactly what is happening. You seek at the beginning, you read the values. And so remember the query where I want a distinct device ID. I seek to the beginning, so I have a device ID. And then I read the next value and I see the same device ID. So I will not continue to look at all the timestamps for this device ID. I will just seek for the next device ID. So just taking the byte representation of the device ID and just looking at the next one. And I seek to it. Maybe it doesn't apply to my where clause, and then seek to the next one. So basically, jumping from one value to the next value. Even if there are multiple entries with the same value, I just skip to the next value until the end. So we call that internally an hybrid scan because it can combine many operations like getting the distinct values or looking at different points with an in list or equal any, or looking at different ranges. And basically, it seeks to the first value, next to get the row, and then just increment the value from the previous row to seek into the next one. So you can see the time complexity of it doesn't depend on the size of the table because this part can be huge. We just skip them. The time complexity of it depends on the number of seeks that you do. So the number of distinct values, for example, when you select distinct, or the number of distinct value of the first column when you have a query that filters only on the second column of the index. And this feature doesn't exist in Postgres. Let's have a look at the Postgres wiki about it. So of course, maybe one day it will be implemented. it is more important in a distributed SQL database, because in a distributed SQL database, if you cannot skip for multiple point queries, for example, then you have to do multiple RPCs to the storage. For a monolithic database, even if you read all rows, it may be just reading buffers from the shared buffer or from the file system buffer. And the OS optimized that also with prefetching, so that you don't see the same difference. But many traditional databases have implemented that. It's called loose index scan in MySQL. It's called index skip scan in Oracle. Well, that's the concept. But in Oracle, index skip scan can be used for the second query I did, like, sorry, I'm disconnected. I will not reconnect again. In Oracle, the index skip scan will be used if you have a filter on the second column of an index and no filter on the first. Then it can do this skip. But for example, in Oracle, I don't think this is used for select distinct, for example. Select distinct has to read all values and build a hash table to get the distinct value, for example. So this exists also in SQLite. Cockroach, I'm not really sure it exists in my test. It just doesn't work. So the Postgres wiki, I don't know, maybe has seen something about it. We can have a look if, yeah. Probably in very specific cases, but not in select distinct. I tried all that. It just scanned all the rows. In DB2, I didn't know that. It's called hybrid. No, in DB2, it's called gem scan, and in Yugabyte, hybrid scan, because that's the name of the iterator that is behind this. So, of course, you can work around it in databases where you don't have that. So this is an example with recursive query. Doing those things, you can do that with a recursive query, getting the next value each time. But this would not be optimal in a distributed SQL database, because then each recursion would be a different call to the table. And we want to avoid that. So this is probably the reason why it's more important to have this feature in Yugabyte than in Postgres. And if you look at the execution plan, Yugabyte is Postgres compatible, which means that you don't have a lot more to learn for reading an execution plan. You see the similar execution plan to Postgres, but with more information. In Postgres, when you want to know exactly the work done, you ask for the number of buffers. In Yugabyte, we don't have buffers because we cannot share buffers between multiple nodes. You cannot scale out the shared buffers. So we have dist, which gives more statistics about the distribution of the query, basically the request to the storage. And you can see that even if my table has many rows, millions of rows, I send a request to the storage only once for this query, because everything is done, is offloaded to the storage, is pushed down to the storage. So that's the thing to look out to know if this feature occurs. With this feature, an index scan returns only the distinct value. And this unique operation, just get them, they are already unique. Without this feature, the index scan would have returned millions of rows, which would be operated, deduplicated by the unique operator. So the number of rows there is gives an idea of the usage of this feature. And only one RPC, that's the most important, yeah. So I said two reasons. Very nice feature, but also I got some users asking me, is it true that there is no optimization in the distributed storage for YugabyteDB? Because that's what Cockroach told them. And I've also seen some webinars from Cockroach where they they say that reusing the Postgres code, as Yugabyte does, is kind of a forced marriage. And they think that by reusing Postgres, we are so tied to Postgres that we cannot optimize the distribution, and that's wrong. And this feature is an example of it. A feature that doesn't exist in Postgres is possible in Yugabyte. There is no constraint by the fact that we reuse Postgres, and that's really important. Actually, the point is that we reuse Postgres because we don't want to reinvent many features like stored procedures, partial indexes that already exist in Postgres and can just be used as is. All the focus is on the optimization, but we reuse Postgres from a fork, which means that, of course, there is a lot of code in it that is added to it to make it cluster aware. The query planner, for example, must know about the remote calls. So we use Postgres, we merge with the new versions of Postgres, but we have a lot of optimizations on it. Do not think that this architecture limits anything in that. That's the opposite, actually. It gives a good Postgres compatibility with many features and still allows all those optimization like we see there. Probably this misunderstanding comes from the fact that we are quite proud of this architecture because it was not easy to do it and plug Postgres at the right level in the distributed storage and transaction layer. But now that it is there, we get all the benefits of it. So the advantage of using Postgres is that we don't need to reinvent all the features that are there. User-defined functions, stored procedure triggers, expression indexes, extensions like row-level security, PG crypto. All this comes for free from Postgres. And then the Yugabyte engineers can focus on the real innovation, not reinventing the features that already exist in an open source database, just focus on the innovation, that is the optimization for distributed SQL, pushdowns, offloading, some filtering, some aggregate to the storage. If you compare, CockroachDB decided to rewrite Postgres in Go, and they still have a lot of work. Probably one day they will have stored procedures, but they need to recode all that. They don't have triggers. I think that they have implemented a few things like expression indexes, but that is slow when you rewrite everything, especially in a different language. The idea of Yugabyte is really to have this Postgres compatibility and more optimizations on it with pushdowns, expressions, aggregates, distincts, as we have seen. So in this architecture diagram, I really add something else in the distributed and transaction storage layer. We not only have the replication and sharding and load balancing, we also have a lot of optimizations there. And more will be coming. So yeah, just I mentioned that I checked in CockroachDB. Basically, the queries I've run there, if you run that on CockroachDB, you will see the same time as a full scan. So basically, there is no skip scan, at least for those queries. I don't know if internally there are some, but the basic things like a distinct on the first column of an index or a filter on the second column of an index, this is really where in Yugabyte you have a time that is much lower than a scan of the whole table. In Postgres, you don't have it. It's not so long to scan millions of rows from memory in Postgres. Basically, I've run this just on my laptop, which is different from the test I did before that was on the Yugabyte cloud. This was just to compare the difference between the different queries. So yeah, something quite important. applications are built for distributed SQL, applications that are built for distributed SQL are probably not doing the same kind of data modeling as we have seen in traditional databases. Typically for this table, in a traditional data model, I would have a table of devices with the device ID and maybe a name or something else. So I don't need in a traditional database with this traditional data modeling, I don't need more optimization to get a distinct device ID, because if I have a table with it, I just read those 10 rows from this table. The problem comes with the scalability of it, because if you have this table, then you have foreign keys, you have to update it. In scale out applications, we try to have less tables, avoid foreign keys, avoid secondary index, so that we have only one structure that is easy to shard and to scale out. And same with the event timestamp. If I have queries on event timestamp without a device ID, I don't want to maintain a secondary index for that. I just want to use the same structure, and this helps. So basically, in traditional databases, I would have multiple tables, foreign keys, secondary indexes. Here, I can do the same and have a scale-out model with a single structure, the primary key of the table. And yeah, just a note, you may have heard that when you design your indexes, you should put the most selective column first in an index. Here you have an example that when you have this feature, this index loose scan, you don't really need this rule, because here I have started with the device ID and then I add the timestamp that is more selective. So really depend on the number of queries that you have. So that's all for that. All the code that you see in those slides, you can run that yourself. This is what I've done in the cloud, the managed YugabyteDB in our cloud, and test it. There will be more and more features, more and more push down. If you port an application written for Postgres or Oracle or anything, if you port it to Yugabyte, and if you find some queries that are slower, please tell us. We have a Slack channel, we have Git issues, and this will help to give some priority on those optimization, those push downs. The goal of being Postgres compatible is to be able to just change the connection string from Postgres to Yugabyte. But then maybe you have to think about the indexing, and maybe we still have some more features to add to optimize all that. So please contact us. YugabyteDB is free. It's fully open source. And then the community helps to improve the product. Thank you very much. And this is a recorded session, but I will be live for questions. So do not hesitate if you have questions. And you can also easily find me on LinkedIn, on Twitter, in many places. Thank you very much, and enjoy your Distributed SQL Summit.